aberration. So you see that there are colored edges, and these colored edges are because of chromatic aberration. The focal length of a lens depends on the refractive index of the material. Refractive index for different wavelengths is different, and hence focal length is different for different colors. It can be corrected by taking combination of lenses with different materials. Such lens is called achromatic lens. So when you take, for example, achromatic aberration, lens maker's formula tells you that 1 by f is n minus 1, 1 by r1 minus 1 by r2, where r2 is the focal length of the second lens and it is negative, and therefore actually suppose r1 is 10 millimeter, r2 is minus 10 millimeter, this will be a positive number. The refractive index of the material of the glass depends on the wavelength. Okay, just a minute. Yeah, which is given by Cauchy formula, that refractive index is A plus B by lambda square. A and B are constants here, and lambda is the wavelength. So you observe that as lambda becomes larger, that is red wavelength, okay, lambda becomes larger, B by lambda square becomes smaller, and therefore refractive index becomes small. If refractive index becomes small, this number becomes small. So 1 by f becomes small, and therefore f becomes large. So you see that red has larger focal length. If lambda becomes small for blue ray, b by lambda square will become large, therefore refractive index will become large, therefore n minus 1 becomes large, therefore 1 by f becomes large and f becomes small. So focal length for blue is smaller. So focal length is dependent on wavelength for a lens. Now this is achromatic doublet. So what you are doing is you are using two different lenses with two different refractive indices, and they behave in such a way. One is convex lens, one is this concave lens. So one tries to converge the rays, one tries to diverge the rays, and what you have done is you are using two different materials, okay, so that the red and blue both will have the same, effectively same focal length. So this is called chromatic doublet. Now how do you get chromatic doublet? So when two lenses are used in contact, the effective focal length is 1 by f is equal to 1 by f1 plus 1 by f2. We have already derived this. So this is lens combination. And if they are in contact, therefore that minus d by f1 f2 is absent term here, because that they are in contact. D is touching, d is 0. Now you can write 1 by f as, for first focus, it is n1 minus 1 into rho 1. Rho 1 is at 1 by r1 minus 1 by r2 for the first lens. Similarly, for the second lens, it is n2 minus 1 into rho 2. Rho 2 is again that the parameter that depends on radius of curvature. So rho 1 and rho 2 are that 1 by r1 minus 1 by r2 for first lens, and rho 2 will be 1 by r1 minus 1 by r2 for second lens. Okay, so that shape is going to remain fixed. What we want is focal length for red and focal length for blue must match. Okay, we want that focal length for red and focal length for blue must match. Therefore, red and blue will come together. So what we want, therefore, if 1 by fr should match with 1 by fb, 1 by n for red. You see, refractive index depends on red color. So for red, refractive index will be different, for blue refractive index will be different. Rho 1 and rho 2 are not going to be dependent on wavelength. Why rho 1 and what are rho 1 and rho 2? They are shape factors. They will depend on the shape factor. They will depend on 1 by r1, 1 by r2. So rho 1, rho 2 do not depend on wavelength. So now what we see, let us apply this for red wavelength and let us apply this for blue wavelength. So left hand side is for red wavelength. N1 r minus 1 into rho 1 plus n2 r minus 1 into rho 2. Now n2 is refractive index of red for the second lens. N1 is refractive index for red for the first lens. See that first lens and second lens will have different materials. We are using two different lenses with different materials. They are cemented together. Here N1b minus 1 rho 1, N2b minus 1 rho 2. And we want this equal to this. Now let us rearrange the term. So put the terms having rho 1 together. what we get, you can take this term on the left hand side, you can take this term on the right hand side. Effectively you get rho 1 by rho 2 equal to minus n2b minus n2r upon n1b minus n1r. This is just a algebraic manipulation. Okay, you can write this formula and do that. I will be sharing the slides. Now we specify, so we have to come to this. We will come to this. We can specify the focal length of achromatic doublet for a mean color. Okay, what is the mean color between red and blue? Say green or yellow. So typically people decide it for yellow. So 1 by focal length of yellow can be written as n1 yellow minus 1 into rho 1, and 1 by f2 yellow equal to n2 yellow minus 1 into rho 2. So this is focal length decided for yellow. So this is focal length decided for yellow. Okay. So what we have is rho 1 by rho 2. This is for yellow color. Okay. We are not talking right now talking about that doublet. We are talking about for yellow color, rho 1 by rho 2 should be n2y minus 1 into f2y upon n1y minus 1 into f1y. See that rho 1 is 1 upon f1y into n1y minus 1, and rho 2 is f2y into n2y minus 1. So rho 1 by rho 2 will be this. They are inversely related. Okay. Now we are going to equate this with this. Okay, we are going to equate this with this. So let us do that. So you have f2y upon f1y, okay, is rho 1 upon n2y minus 1, and here what we have, rho 2 upon n1y minus 1. But by equating this part with this part, we get this relation. Okay, again a algebraic manipulation you can do. Now see one thing here, the numerator contains everything for second lengths, denominator contains everything for first lengths. So that is something very important. So what is this numerator here? It is refractive index for blue color minus refractive index for red color divided by refractive index for yellow color minus 1. The denominator is also same, refractive index for blue color minus refractive index for red color upon refractive index for yellow color minus 1. Okay, this is for second length, this is for first length. So what we can then do is this quantity, refractive index for blue color minus refractive index for red color upon refractive index for yellow color minus 1, is called dispersive power of the material. And now what we can say is,
Sorry sir, can you please repeat the last step? I did not follow.
see this, we have equated rho 1 by rho 2 equal to this with this. So when you write this right hand side equal to that right hand side of this, what we get is this equation. This
Sir,
is
but why blue and red?
because you see here blue and red is there. See,
Sir, matlab blue
ultimately what do we want to do?
given
What
to us,
we want to do
all we
is,
have to
yeah,
find it.
yeah.
A blue or red would be given to us in the problem itself.
No, no, right now I'm not coming to problem. Right now let us look at this, that suppose you know what is the refractive index of blue, you know what is the refractive index for red, you know what is the refractive index for yellow, you know all that. See, in reality when you are designing a lens, you have taken some glass. That glass you are going to study, so you will find out what is the refractive index of blue for that glass, what is the refractive index for red for that glass, and what is the refractive index for yellow for that glass. So you are a lens maker. So you already have taken some material whose refractive index for blue, red and yellow you already know. Knowing that, you are going to design two different lenses, one convex lens, one concave lens, in such a way that they should fit to each other and effectively work as a convex lens. Okay.
Sure, sir. Got it.
And then what you are going to do is you are designing it in such a way that the blue rays and red rays must come together after passing through this lens combination. You want to design this kind of a lens. So when you want to design this kind of a lens, effectively what you realize is the focal length for yellow of second lens and focal length for yellow of the first lens should match. This ratio should be equal to this ratio. This
Yes, sir.
number is called dispersive power. This number is called dispersive power. Negative, there is a negative sign over here, and this negative sign implies what? It implies that one of the lens has to be concave lens, because concave lens has negative focal length. The number is not going to be negative. This number is not going to be negative. For all materials, the refractive index for blue is always greater than refractive index for red, and refractive index for yellow is always going to be, I mean, any refractive index for a material is always going to be greater than 1. So numerator is greater than 1, I mean positive, denominator is positive, therefore dispersive power is always positive. The point is, the focal length for yellow of the second lens and focal length for yellow of the first lens, this ratio is negative, indicates that one of the lens has to be concave lens. So why that concave lens was shown here in the earlier diagram, here, that condition comes from this condition. Now people don't give dispersive power. Generally when you look at different kind of materials, people give reciprocal of dispersive power, because dispersive power is a number in fraction, 0.022, 0.035, something like that. So people prefer number which are not small numbers. People prefer numbers which are the reciprocal of dispersive power. So that is called V number, or it is also called dispersive index, or it is also called Abbe number, because Abbe studied many of these. Abbe was a physicist who studied many of these things. So here is a table. So suppose I am going to give you a problem, I will give you numbers from this table. Now there are different kind of materials given over here. So borosilicate crown glass of a different number, BAC1, BAC2, then crown flint glass, barium crown glass, dense barium crown glass, and so on. So people make glasses of various categories. What is shown over here, ND, is the refractive index for yellow color. N is refractive index, suffix D. D stands for sodium D line. Sodium D line means that sodium vapor lamp, 5893 angstrom average, or 589.3 nanometer. For that wavelength, so this is basically refractive index for yellow color. If you use crown glass, it is about 1.5. If you use flint glass, it is around 1.6. Okay, dense crown glass is 1.6. If you use flint glass, then it becomes slightly different. Okay, you may use extra dense flint glass, it will be 1.66. It can go to 1.7. Okay, and this is the dispersive index. For borosilicate, it is 63.5. Then if you use flint glass, it is 53. So smaller dispersion. You see why flint glass is preferred, because it has got smaller dispersive index. Okay, and no, the dispersion, but then in that case dispersive power will be large. So you may use a good combination of both these. So here what people do then is, this is the achromatic combination, that you use nice combination so that you get appropriate the two wavelengths matching each other. The red and blue will match together here, but the green will not exactly match, but that's fine. Most of the times it is okay. You can have more complicated lens. You can have something called apochromatic lens, where what is happening is all three colors, three edges, the red, blue, green, all three of them will come to the same focus. So this is called apochromatic. So high quality microscope use apochromatic lenses. Okay, most of the microscope that we have uses achromatic combinations only. We don't generally go for apochromatic, because apochromatic becomes more expensive. and the things become more expensive because people design special kind of glasses. People design glasses so that when the temperature changes, the focal length shouldn't change because the glass will expand, contract, the shape should not change, and you are going to cement the glasses together. So that material also should have such a kind of refractive index that it should not cause its own problems, its multiplication, its multiple reflections. See, every surface when you are joining the glasses, every surface, every boundary will cause some amount of reflection. So you need to design it in such a way that the material should be so good that you many times prepare artificial material, special kind of glasses, and all this research is sponsored by these companies which are manufacturing microscopes or manufacturing optical instruments, and because they are sponsoring, they are putting money to enhance the quality. Most of this is patented, and therefore it is not easily available, and that patent amount makes it expensive. So people go for apochromatic lenses these days, but they are expensive for that reason. Okay, and of course every patent will have its own lifespan. So after 20 years generally that patent information is available, so within 20 years the company is going to earn the money. Okay, but then after that, by that time the company will come out with even better technology. So then the apochromatic lenses of that old technology may become relatively cheaper. Okay, but then if you are okay with that kind of a instrument, then it is fine. But if you are interested in the what you call state of the art, okay, the latest technology, then obviously the expenses go high. So that's basic about reducing the chromatic aberration, that one uses achromatic combinations, and one can even go for apochromatic combinations, but achromatic combination is something that one can relatively easily do, and one can look at the simple mathematics involved, and something that involves dispersive power, and we should be able to do at least some simple numericals based on this. It you will use multiple things. It will use uh, understanding of dispersive power. It will use the lens maker formula over here. Okay, what is the effective focal length, and we will talk about the radius of curvature. So you see that this radius of curvature and this radius of curvature for the first lens, second radius of curvature, second lens, first radius of curvature are same. Okay, then so we will talk about these kind of problem in my problem sheet. Okay, so we end at this point.